Hello, and this is a test video on finding ways to present mathematical content as part of a project to help perhaps improve the online presence of mathematics and statistics support. I'm just doing a specimen kind of lecture, if you will, on the polar form of complex numbers. So I'm recording with my webcam right there in 720p, and there's me here, hello, with a whiteboard, which I'm going to be doing some presenting on, and just to see how it works. Okay then, let me just turn this light off. You'll have known previously that complex numbers can be written in the form x plus iy, where x and y are both real numbers, like that. That's called the rectangular form of complex numbers. The rectangular form of complex numbers. However, that is not the only way to express a complex number. And to think about it geometrically, let me draw a diagram. Okay, this axis is the imaginary part, and this axis here is the real part of any complex number z. This is the origin, and this is called the Argand diagram, or the complex plane. And any complex number can be represented in it geometrically by a point, rather like the xy Cartesian axes. Let's say we have this complex number here, z equals, let's say, 3 plus 2i. Then we have 3i on the axis there, the imaginary axis, and then we have, it should be 2i, sorry, and we have 3 on the real axis here. We have a complex number here which can be linked to the origin. And with this form we can apply some knowledge of right-angled triangles. You'll notice that this is a right-angled triangle, and we can have an angle here, theta. We also define something called r, which is the length, the geometrical distance of the complex number from the origin. And with this we can define some new formulae. The modulus of a complex number we write as z with absolute value bars around it. And we define this as, let's say z equals x plus iy, z1. We define this as x squared plus y squared, because if that distance is x and this distance is y, it follows immediately from Pythagoras' theorem. We can also define the argument, well, modulus is called r, we also define the argument as theta, and this is the angle z makes with a positive real axis. Okay, and when the complex numbers are in this quadrant, where the real and imaginary parts are both positive, we define the argument as the inverse tan of y over x when x and y are both greater than 0. And how this relates to the polar form, I'll explain. Any complex number can be written in the following form. We can rewrite z as r and then cos theta plus I sine theta. This is called the polar form or the modulus argument form of a complex number z. And it immediately follows from this definition. Suppose we have x, and if we just relate it using basic trigonometry, x is r cos theta, and we have y equals r sine theta. Plugging those into that formula will immediately give you this. And an example of this we can apply with z equaling 3 plus 2i, for the example above. Because y and x are both positive, it's easy to evaluate the argument. Theta is equal to arctan 3 over 2, which we can calculate fairly easily, but I don't have a calculator with me, but let's just call that omega, little omega. R is equal to the Pythagorean sum of 3 and 2, so root 3 squared and 2 squared. That is 9 plus 4 equals root 13. That means that the complex number can then be written. Let me just create some extra space. Z is equal to root 13 cos omega plus I sine omega. Okay, that's an example of the polar form of complex numbers, how it can be applied. Thanks for watching this video, and any feedback or thoughts on the format of the video will be very helpful. It'll allow me to advance in the project a bit further and determine other means of communicating mathematics. So thanks for watching.